Hi class, in section 2.5, we are dealing with more applications of exponential functions and derivatives. In this section, we're specifically dealing with exponential decay. That is, we're finding functions that satisfies dp dt, where your rate is negative, so negative k times p. We're going to convert between decay rate and half-life, and we're going to solve applied problems involving exponential decay. Let's get started. We have the equation dp dt is equal to negative kp, and we know that that solution will be p of t is equal to p naught e to the negative kt, because this is really the same equation that we did in section 2.4. The only difference is that my constant is negative this time. And so while the section 2.4 talked about exponential growth because it was a positive growth k, then we have exponential decay because my constant is negative. Strontium-90 has a continuous decay rate of 2.8% per year. The rate of change of an amount, N, of this radioactive isotope is given by dN dt is equal to negative 0.028 N. The first question asks us to find the function that satisfies this equation. First of all, let's recall the equation from the previous page. We know that it would have this related equation, p of t is equal to p naught e to the negative kt. We're asked to allow n naught to represent the amount present at time equals 0. This portion right here represents our negative k. So negative k is equal to negative 0.028. And so we're going to put that into this equation. Therefore, we want to call it n of t is equal to n naught e to the negative 0.028 t. For part B, it's asking us to replace n naught with 1000 and then to replace t with 70. So knowing that n of t is equal to 1000 times e to the negative 0.028 t, now let's find n of 70. Using my calculator, I get approximately 140.858 grams. We can say that there's approximately 140.858 grams of strontium-90 after 70 years. Part C asks us to find the rate of change of the amount of strontium-90 after 70 years. So first, we have to take the derivative of n of t. So n prime of t would give us 1000 times e to the negative 0.028 t, and then the derivative of that would be negative 0.028. And so multiplying that out would give me negative 28 e to the negative 0.028 t. And then we want to find n prime of 70, negative 28 times e to the 0.028 times 70. Let's use our calculators to find that number. I get negative 3.944. How do you know the units on this answer? We go back to this question. It says dN dt. That's a change in n over the change in t. N is how much radioactive isotope we have in grams, and t is how many years. So we're declining by 3.944 grams per year. All right. Part D asks us, after how long will exactly half of the original 1000 grams remain? Well, if we start off with 1000 grams and we want exactly half, we're going to end up with 500 grams. So we can set this up to ask ourselves how much time we're going to be solving for t. For this equation, the first thing we want to do is divide both sides by 1000. You end up with 1/2 on this side. E to the negative 0.028t. Now, I just want to point out something. Sometimes they might ask you the same question, but they won't give you the original amount nor how much you have. But that's okay. No matter what you start off with, if they want to end up with exactly half the original amount, you start off with 1/2 on this side and a 1 coefficient here. And so we can solve this. This is an exponential problem, but we want to isolate the t. So we're going to rewrite it as negative 0.028 t is equal to natural log of 1/2. Now recall that natural log of 1/2 could be written as natural log of 2 to the negative 1 power, and that could be written as negative ln of 2. And if I want to isolate the t, I would get t is equal to negative ln of 2 divided by negative 0.028. Those negatives can cancel out, so you would just have ln of 2 over 0.028. And my calculator gives me 24.755. We solved for t. T measures how many years, so this is approximately 25 years or 24.76 years. The half-life of strontium-90 is 24.76 years, and that's when we will have exactly 500 grams remaining. Our work in the previous problem should lead us to this theorem, is that the decay rate times the half-life gives us natural log of 2. That is, if we want to solve for the decay rate and we know how long the half-life is, then we can say k is equal to natural log of 2 divided by t. Or if we know the half-life and we want to know the decay rate, then we take natural log of 2 divided by k. And so knowing that k times t is equal to natural log of 2 helps us solve for either k or t depending on what our needs are. Let's see how this theorem can help us in the next problem. In video example 2, we have the decay rate of cesium-137 is 2.3% per year. So our k would be 0.023. And then it asks, what is its half-life? And so we're solving for t. We need to find that. And we know that k times t is equal to natural log of 2. So keeping the t here, we want to take ln of 2 and divide by k. In other words, we're taking natural log of 2 and dividing by 0.023. My calculator tells me that that is 30.1368. So we can say approximately 30.1 years. Notice I'm getting years because the decay rate was given per year, so that's how I know it's in years. Part B asks us about the half-life of barium-140. It tells us that the half-life is 13 days. So we have 13 days here as our half-life. What is the decay rate? Once again, we know it's k times t is equal to natural log of 2. And so solving for k, we're going to divide by t. And that means we're going to take ln of 2 and divide by 13. Our calculator tells me that's approximately 0.053. And so that translates into 5.3% per day. We always want our units to match up. Since the half-life was given to us in terms of days, then we're going to do our decay rate in terms of days. For video example 3, it asks us, the radioactive element carbon-14 has a half-life of 5,730 years. The percentage of carbon-14 present in the remains of plants and animals can be used to determine age. How old is a skeleton found at an archaeological site if tests show that it has lost 60% of its carbon-14? Well, in order to solve this question, the first thing we want to do is find the decay rate. So, setting this up, we know k times t is equal to natural log of 2 k is going to be natural log of 2 divided by t, which is going to be natural log of 2 divided by 5730. And then using our calculator, we can come up with approximately 0.0001297. Alright, now that we solved for k, we can use it in our formula to figure out how much we've lost. Now, we're assuming we start off with 100% of the carbon-14. So the initial amount is going to be 100%. In other words, that's going to be 1. But then, how much are we going to have after I've lost 60%? If I've lost 60%, then I'm at 40%. In other words, I'm going to be solving for 0.4. So to do part B, we needed to do a little bit of side work, but I'm going to say how much time, what is my t, if I'm left with 0.4 of my original carbon-14. Looking at this equation I have written down, I have 40% left, starting off with 100%, and then we have e to the negative 0.0001297 t. And so dividing both sides by 1 just makes that 1 disappear, and then we're ready to rewrite this as a natural log. So pulling that power down, I get negative 0.0001297 t is equal to natural log of 0.4. And then solving for t, you're going to take natural log of 0.4 and divide by that negative 0.0001297. And let's let our calculator figure that out for us. We get 7574.5. And what number is this? If we look at this, this would be in years. So it would take approximately 7,574.5 years for it to decay this much. Therefore, the skeleton is 7,574.5 years old. You always want to make sure that your answer answers the question and how it was asked. So since it asked how old is the skeleton was 7,574.5 years old. For question number 4, it says, following the birth of their granddaughter, 2 grandparents want to make an initial investment of P0 that will grow to 10,000 by the child's 20th birthday. Interest is compounded continuously at 6%. What should the initial investment be? Well, notice we have a hint here, but even if we weren't given that hint, is this exponential growth or exponential decay? Do they want to put money in and lose the value of that money, or do they want that value to grow? And so, because we think we want that value to grow, we're going to use the exponential growth model. We know that the interest is compounded at 6%, so our k is 0.06. We're going to put that in this model, and then we don't know how much to put in initially, but we know that we want it to be 10,000 at the end. So the end amount should be 10,000. And we also know that we want this to happen by the child's 20th birthday, so our time will be 20 years. And so we have enough information to put into this equation. We're going to say 10,000 is equal to P0 e to the 0.06 times 20. Now we just want to solve for P0, so we're just going to divide both sides by e. And we have e to the 0.06 power times 20, and that's going to equal to P0. We go ahead and use your calculator to solve this. So then we get P0 is approximately $3,011.94. And we want to put that units and make sure we go to the right number of decimal places for that answer. So if the grandparents deposit $3,011.94 into an investment account. When the child turns 20, the child will have $10,000. Newton's law of cooling has this formula here that talks about the temperature, capital T, of a cooling object which is dropping its rate that is proportional to the difference T minus capital C, where capital C is the constant temperature of the surrounding medium. What do all those words mean? Let me explain it to you. Capital T is the temperature of an object, such as a hot cup of coffee is maybe 200 degrees Fahrenheit. And then capital C would be the temperature of the environment. Let's say the temperature in the room. That might be 70 degrees Fahrenheit. And so the difference between the temperature of the object and the temperature of the environment is T minus C. And then lowercase t will stand for time, how much time it takes for that 200-degree cup of coffee to drop its temperature until it's the same as the temperature of the room. We're given an equation here, which helps us to put all of these portions into an equation and helps us solve some questions regarding how long has this cup of coffee been sitting out, if we know its temperature now, if we know how fast it's changing its temperature to the temperature of the room, and different things like that. And so we're going to use this to solve the next problem. For this last question, we have a forensics question. A body is found slumped over in a desk in a study. A coroner arrives at 2 a.m., immediately takes the temperature of the body, and finds it to be 92.8 degrees. She waits 1 hour, takes the temperature again, and finds it to be 90.6 degrees. She also notes that the temperature of the room is 72 degrees. When was the murder committed? So we're going to start off with the equation and then see if we can find our way back to what time it started. So I wrote up here the equation that we're going to be using, and we only know one of those values currently. We know that C is the temperature of the room, which is 72 degrees. We don't know A, we don't know K, and then the T is something that we will be solving for. So one of the things we want to do is say, when she first gets there, we're going to call that time 0. That's at 2 a.m. And then 1 hour later, when she tries the temperature again, that would be 1. Or 3 a.m. The value of time would be 1. The temperature of the body at time 0 was going to be 92.8 degrees. And the temperature of the body 1 hour later is going to be 90.6. And then writing the equation using t equals 0 and t naught equals 92.8. This is what we get. And then subtracting 72 from both sides would give me 22.8 is equal to a times e to the 0. And e to the 0 is just 1. So that's easy for us to solve for a. So that gives us one variable. And then we want to take this a and the information over here and this c to solve for k. So we're going to set this up again. 90.6 is equal to 22.8 as my a, e to the negative k times t of 1 plus 72. So subtracting 72 from both sides gives me 18.6. And negative k times 1 is just negative k. We'll rewrite it as 18.6 divided by 22.8 is equal to e to the negative k. And to solve for k, and we'll get negative k is equal to natural log of 18.6 over 22.8. Notice that I'm keeping the fraction instead of rewriting it. That's because I want my answer to be as exact as possible. So this is what I'm going to type into my calculator. So that gives me approximately negative 0.20359. And so k is going to be positive 0.203 0.59895552, keeping as many digits as possible for this question. One thing that this question does not tell us is that the temperature of the body before it died should be 98.6 degrees Fahrenheit. So if we want to find out when the murder was committed, we're trying to find out when was the temperature of the body this. Let's recall that our C is 72 degrees and that our A was 22.8 and our K, we're going to just estimate it to be 0.2. And so plugging that into our equation, we get 98.6 is equal to 22.8 e to the negative 0.2 t plus 72. So solving this would give me 26.6 taking natural log of both sides. My calculator says then that t is approximately negative 0.77, and that would be hours. So 0.77 of an hour is approximately negative 46.2 minutes. So that would mean the murder was committed about 46.2 minutes before 2 a.m. So it was probably, the body was probably killed at 1:14 a.m. So working backwards, if we start at 2 a.m. and we want to subtract 46 minutes from that, we would get the approximate time of death to be at 1:14 in the morning. Okay, let's go through the steps again. We first started off with taking the temperature at time 0, and that was 92.8. And then we took the temperature at time 1, and that was 90.6. And then we know that we have a temperature of 98.6, but we were saying what time did that happen at? And then once we figured out what that time was, then we have to go back from the 2 a.m. and go to 1:14 in the morning. That's when the murder was committed. All right. So on that bright, happy note, you guys can do CSI stuff now. We have this type of question with the Newton's law of cooling and some other exponential decay that we were doing in this section. Go ahead and get some practice in. This is the last section of the chapter that we're going to be doing. And so we're now done with chapter 2. Thank you and have a good day.